Hey, so we're about to tackle trigonometry. And I know that word can sound a little intimidating, but stick with me here because by the end of this, you're going to see it for what it really is, a super elegant and powerful tool that you can absolutely get the hang of. So let's just jump right in with a puzzle. How in the world do you measure the height of a massive mountain without actually climbing it? Or, a giant skyscraper without some impossibly long measuring tape? Sounds kind of impossible, right? Well, the answer isn't some kind of magic. It's math. It's trigonometry. And the secret to unlocking all of this incredible power doesn't start with a bunch of complex formulas or weird-looking symbols. Nope. It all starts with one single, really simple shape. And that brings us to our first big idea, the building block. Because really, to understand how we can measure the entire world, we first have to get to know the one simple shape that, in a way, builds it all. And here it is, the right triangle. Seriously, that's it. When you boil it all down, trigonometry is just the study of this one specific shape. It's about the predictable, super reliable relationships between its sides and its angles. And that perfect 90-degree corner, that's what lets us build things straight and measure things that are super far away. Okay, so we have our shape. Now we need to learn its language. This next part is all about getting the vocabulary down, the specific words we use to talk about the sides of a right triangle. First word, and it's the most important one, hypotenuse. This is always the longest side, and you can find it just by looking directly across from that 90-degree right angle. Think of it like the triangle's anchor. It's the one side that never changes its name, so always find this side first. Okay, simple enough, but what about the other two legs of the triangle? Do they have fixed names too? Well, nope. And this right here is probably the most important idea in all of basic trigonometry. The names of the other two sides aren't fixed. They completely change depending on which corner of the triangle you're looking from. Your perspective is literally everything. So let's define them. From whatever angle you're focused on, the opposite side is, well, it's the one all the way across the triangle from you. And the adjacent side is the one right next to you. That isn't the hypotenuse. I mean, adjacent just means next to. It's that simple. Let's see this in action. Imagine you're standing at that bottom left corner. From that viewpoint, the side way over there across the triangle is your opposite. And the side right next to you is the adjacent. Makes sense, right? But now, watch what happens. If you just walk over to that other corner at the top, everything flips. All of a sudden, the side that was adjacent is now opposite you, and the side that was opposite is now right next to you, making it adjacent. This is the big aha moment. If you can get this flip down, you've honestly mastered the hardest part. Okay, on to section 3. So we've got our shape, and we've got the language to describe it. Now we can finally figure out what those famous, and maybe a little scary, trig words actually mean. Sine, cosine, and tangent. So here's the big secret. Sine, cosine, and tangent, they aren't magic. They're not some abstract, crazy concept. They are just names we give to 3 different ratios. They're just fractions, comparing the length of one side to another. And here's the real magic. For any specific angle, like, say, 30 degrees, that ratio is always the same. It doesn't matter if the triangle is tiny and fits in your hand, or if it's the size of a mountain. That consistency is what lets us measure the entire universe. First up is sine. The sine of an angle is just the length of the opposite side divided by the length of the hypotenuse. You can think of it as asking a question. Compared to its long, sloping side, how tall is this triangle? Next, we have cosine. This time, it's the ratio of the adjacent side to the hypotenuse. So if sine measures the tallness, you can think of cosine as measuring the wideness or the horizontalness of the triangle, again compared to that same long, sloping side. And last but not least, tangent. Now, notice something's missing here? The hypotenuse is gone. Tangent is the ratio of the opposite side to the adjacent side. It's a direct comparison of the triangle's height to its width. And you might already know that by another name, slope or rise over run. All right, let's just pause here for a second and see it all together. Sine is opposite over hypotenuse, that's our tallness ratio. Cosine is adjacent over hypotenuse, our horizontalness ratio, and tangent is opposite over adjacent, that's pure slope. These 3 are our fundamental tools. Now, trying to memorize all of that, opposite over this, adjacent over that, it can feel like a lot. But don't you worry, because math has given us the ultimate cheat code, a tool so brilliant it packs this entire system into one easy-to-remember word. And this is it, SOHCAHTOA. Go ahead and say it out loud, it really helps. SOHCAHTOA. This little mnemonic is the key that unlocks everything we just went over and makes it pretty much impossible to forget. Let's break it down really quick. SOH just tells you that sine equals opposite over hypotenuse. CA tells you that cosine equals adjacent over hypotenuse. And TOA tells you that tangent equals opposite over adjacent. See? It's all right there, perfectly organized. So for our final section, let's actually put this awesome tool to work. Let's see how SOHCAHTOA helps us unlock a real trigonometry puzzle. Okay, picture this. You're looking at a right triangle. You know how long the side adjacent to your angle is, and your goal is to figure out the length of the side that's opposite your angle. So you have the adjacent, and you want the opposite. Which one of our three tools, sine, cosine, or tangent, are you going to use? The key is to just look at what you have and what you want. You have A for adjacent, and you want O for opposite. Now just scan your cheat code. SOHK, there it is, TOA. Which part of the code has both an O and an A? TOA does. And that tells you instantly, with zero guesswork, that you need to use the tangent function. It really is that straightforward. And that really just brings everything together so perfectly. Learning the definitions, opposite, adjacent, and hypotenuse, that gives you the map of the triangle. But SOHCAHTOA, that's your compass. It's what lets you navigate that map, pointing you in exactly the right direction every single time. So now that you have the compass, what are you going to go measure?
All right, we're going to tackle a subject that, let's be honest, sounds pretty complicated. But I promise you this, by the end of this explainer, you're going to see trigonometry not as some scary math class, but as a secret code for understanding and measuring the world all around you. Yeah, that word, trigonometry. It's got some heft to it, doesn't it? If you've ever felt a little knot in your stomach just hearing it, you are definitely not alone. But what if I told you it's way, way simpler than it sounds? Because if we just break it down to its Greek roots, the secret is right there in the name. Trigon just means triangle, and metry means measurement. That's it. That's the whole thing. We're just talking about triangle measurement. Seriously, nothing more, nothing less. And look, this isn't just about some abstract shapes on a piece of paper. This is a super practical toolkit. It's the math that helps us build massive bridges, design sturdy homes, and even figure out how far away the stars are. You see, triangles are kind of the hidden building blocks of our world, and trigonometry, well, it's the instruction manual. So, here's our game plan for today. First, we're going to step into the world of triangles. Then, we'll learn how to read the map of a triangle. After that, I'm going to give you the secret code that unlocks the whole thing. And finally, we'll see how this becomes the ultimate measuring tool. Sound good? Let's get started. All right, Part 1, the world of triangles. Our whole journey here really just starts with one specific and very, very special kind of shape.
Meet our hero, the right-angled triangle. Its superpower is that one perfect corner, the one that looks exactly like the letter L. Now in math, we call that a 90-degree angle, and it is the foundation for everything we're about to do. So always be on the lookout for that L shape first.
And to see this in the real world, just picture a ladder leaning against a wall. The flat ground and the straight wall, they create that perfect 90-degree corner, right? While the wall, the ground, and the ladder itself, they form a perfect right-angled triangle right there in your backyard. Okay, Part 2, learning the triangle's map. Now that we know our hero shape, we need to learn how to navigate it. And just like with any map, that means learning the names of the key places, or in this case, the sides. Now there are only 3 names you need to learn. The hypotenuse is the easy one. It's always the longest side, the diagonal one that's directly across from that 90-degree corner. The other 2, opposite and adjacent, well, they depend on which corner you are standing in. The opposite side is way across the triangle from you, and the adjacent side is, well, it's right next to you. And this is the part where your point of view changes everything. So, if you're standing at the bottom corner looking up, the vertical wall is opposite you. But if you were to climb the ladder and look down from the top corner, the ground suddenly becomes opposite. The names literally swap. This is so important. It all depends on your point of view, which angle you're looking from. Okay, Part 3, the secret code. SOHCHTOA. You know the shape, you know the names of the sides. Now it is time for the magic words that tie it all together. You've probably seen these words on a calculator, right? Sine, cosine, and tangent. They sound super complicated, but they're not. I want you to think of them as simple recipes. Each one is just a ratio, which is just a fancy word for a fraction that compares the length of one side to the length of another. So here are the three main recipes. Sine, or sin on your calculator, is the length of the opposite side divided by the hypotenuse. Cosine, or cos, is the adjacent side divided by the hypotenuse. And tangent, or tan, is the opposite side divided by the adjacent. See? Each one is just a simple division problem.
Okay, I know what you're thinking. That is a lot to hold in your head. Opposite, over, what now? How on earth is anyone supposed to remember which recipe goes with which name?
With this one, single, kind of strange word, soka-toa. Go ahead, say it out loud. So-ka-toa. This is the secret code. This one word holds the key to remembering all three of those recipes we just looked at. It's the ultimate cheat code.
Let's break it down. It is so simple. SOH tells you that sine is opposite over hypotenuse. CAH tells you that cosine is adjacent over hypotenuse. And TOA tells you that tangent is opposite over adjacent. That's it. If you can remember SOH, KOTO, you can solve pretty much any basic trigonometry problem you'll ever see.
All right, part 4, the ultimate measuring tool. We've got the secret code. Now let's actually put this thing to work.
So what about those sin, cos, and tan buttons on your calculator? The absolute best way to think about them is as simple machines. And I mean really simple. I want you to think of them like a toaster. No, seriously, a toaster does one job. You put something in and something else comes out. Here's how it works. The input, that's the bread, is an angle. Let's say 30 degrees. The machine is your calculator's sin button. You push it. And the output, that's the toast, is the ratio of the sides that always goes with that angle. You put in an angle, you get out a ratio. Simple as that. For example, go ahead and type sine of 30 degrees into any calculator. I guarantee it's going to spit out the number 0.5. But what does that actually mean? It means that for any right-angled triangle in the entire universe with a 30-degree corner, the opposite side will always be exactly half the length of the hypotenuse. That is an incredibly powerful, fixed rule of the universe.
And a rule like that, it turns you into a detective. It lets you find missing information about things you could never easily measure with a tape measure, like the height of a giant tree or the width of a river you can't cross.
With SOH-CAH-TOA, you can do two amazing things. If you know just one angle and one side length, you can find all the other missing sides. Or if you know any two side lengths, you can actually work backward to find the exact size of the missing angles. It's a complete toolkit for solving any triangle. So you see, trigonometry isn't some scary, abstract math. It's a language for describing the shapes that build our world. It's a code, it's a recipe book, and it's a detective's toolkit all rolled into one. The only question left is, now that you have it, what will you measure?
All right, let's talk about trigonometry. If that word alone makes you kind of nervous or gives you flashbacks to high school math, then you are in exactly the right place. Because today, we're going to peel all of that away and get to what this stuff actually is.
This right here, this is the single most important idea we're going to talk about. Seriously, forget the flashcards, forget the formulas for a second. At its very core, trigonometry is just about relationships. And once you see it that way, trust me, everything else just starts to click. And that's the big question, right? What is this magical relationship? Well, it's something that's literally built into the world around us, from designing video games to building bridges. And you know what? It is way simpler than you've been led to believe. So, our first move is to get past this idea of just memorizing rules. We need to focus on the connection. The real story here, the whole point of trigonometry, is seeing how one little angle can decide the lengths of an entire shape. You know, think about opening a door. That's trigonometry in action. The angle you open the door directly changes the distance from the edge of the door to the wall. A tiny angle means a tiny gap. A big angle means a big gap. That's it. That's the relationship. It's really that simple. Okay, so to keep things from getting crazy, trigonometry focuses on one single heroic shape, the right triangle. And this is actually a brilliant move because it gives us a really stable, predictable place to see all these angle and side relationships play out. And inside that predictable world, we have one part we can always count on, The hypotenuse. Think of it as your anchor. It doesn't matter how you flip or spin that triangle, the side across from that 90-degree corner is always the hypotenuse. Its name never changes. Lock that in your brain. Now here's where things get interesting. The other two sides, opposite and adjacent, their names totally depend on your point of view. See the little eyeball there? The side across from your angle is the opposite. The side right next to your angle is the adjacent. But here's the kicker. If you move to the other corner, those labels switch. It's all about perspective. Yes, so katoa. You've probably heard it, maybe even chanted it in class like some kind of weird magic spell. But it's not magic at all. It's just a really, really clever memory tool designed to make all this a whole lot easier. Let's just break the code real quick. SOH just tells you that sine equals the opposite side divided by the hypotenuse. CAH tells you cosine is the adjacent divided by the hypotenuse. And TOA tells you tangent is the opposite divided by the adjacent. See, it's just a shorthand, a simple way to remember those three main relationships. So why does this silly word work so well? Well, it's a cool little brain hack called chunking. It's just way easier for your brain to remember one word, SOHCAHTOA, than it is to remember three separate math formulas. So you're not just memorizing, you're actually helping your brain work smarter. Okay, let's tackle another one of those scary math words, function. Whenever you hear someone say sine function, don't let your brain shut down. A function is really just a simple machine that follows one specific rule. Think about the sine function like this little machine here. Step 1, you put an angle in. Step 2, the machine runs its rule, in this case the SOH rule, right? It takes the length of the opposite side and divides it by the hypotenuse. And step 3, it spits out a single number. That number is called a ratio. And here is the absolute most crucial point of this whole thing. That number it spits out, that ratio, it has nothing to do with how big or small the triangle is. It is only, and I mean only, determined by the angles, by the triangle's shape. Let's prove it. Let's say we have a triangle where the opposite side is 5 and the hypotenuse is 10. Okay, our sine machine does its thing. 5 divided by 10, and it spits out 0.5. Got it. Now, what if we have a tiny little triangle with sides 1 and 2? It's a totally different size, right? But what's the ratio? 1 divided by 2 is, yep, it's still 0.5. Let's go huge, a massive triangle with sides 50 and 100. You already know what's coming, don't you? 50 divided by 100 is, you got it, still 0.5. It doesn't matter if the triangle fits in your hand or is the size of a building. If the angles are the same, the ratio is the same. That is the secret of trigonometry. So this amazing consistency between an angle and its ratio, it creates this kind of unbreakable link. It's like a bridge that lets us travel between two different worlds. And this bridge is a two-way street. Going forward is what we've been doing. You know the angle, and you can find the ratio. That's a normal trig function. But here's the cool part. It works in reverse. If you know the ratio, you can use it to figure out the angle. That's called an inverse function. For example, here's a stone-cold geometric fact. A 30-degree angle in any right triangle on Earth will always create a situation where the opposite side is exactly half the length of the hypotenuse. Always. Which is why the sine of 30 degrees is always 0.5. It's a law of the universe. And once you get that, once you really understand that two-way relationship, you've made a really important shift. You've gone from just trying to learn rules to actually understanding the logic. So just stop and think about what you actually get now. You can look at a right triangle and confidently label its sides from any angle. You can use SOHCAHTOA not as a random chant, but as a logical tool. You get that every angle has a special ratio and that this connection goes both ways. This isn't just about memorizing stuff. This is how you think with trigonometry. And that's really the big idea here. This isn't about just passing a test anymore. It's about having a new way to see and understand the geometry of the world around you. You are officially thinking trig. So you've done the hard part. You've built the entire foundation. This core logic is what everything else, all the other functions, the unit circle, all of it is built on top of. So the question isn't, can I learn this anymore? The real question is, what am I going to build with it?
Hey, so we're about to tackle trigonometry. And I know that word can sound a little intimidating, but stick with me here because by the end of this, you're going to see it for what it really is: a super elegant and powerful tool that you can absolutely get the hang of. So let's just jump right in with a puzzle. How in the world do you measure the height of a massive mountain without actually climbing it? Or, a giant skyscraper without some impossibly long measuring tape? Sounds kind of impossible, right? Well, the answer isn't some kind of magic. It's math. It's trigonometry. And the secret to unlocking all of this incredible power doesn't start with a bunch of complex formulas or weird-looking symbols. Nope. It all starts with one single, really simple shape. And that brings us to our first big idea, the building block. Because really, to understand how we can measure the entire world, we first have to get to know the one simple shape that, in a way, builds it all. And here it is, the right triangle. Seriously, that's it. When you boil it all down, trigonometry is just the study of this one specific shape. It's about the predictable, super reliable relationships between its sides and its angles. And that perfect 90-degree corner, that's what lets us build things straight and measure things that are super far away. Okay, so we have our shape. Now we need to learn its language. This next part is all about getting the vocabulary down, the specific words we use to talk about the sides of a right triangle. First word, and it's the most important one, hypotenuse. This is always the longest side. And you can find it just by looking directly across from that 90-degree right angle. Think of it like the triangle's anchor. It's the one side that never changes its name. So always find this side first. Okay, simple enough, but what about the other two legs of the triangle? Do they have fixed names too? Well, nope. And this right here is probably the most important idea in all of basic trigonometry. The names of the other two sides aren't fixed. They completely change depending on which corner of the triangle you're looking from. Your perspective is literally everything. So let's define them. From whatever angle you're focused on, the opposite side is, well, it's the one all the way across the triangle from you. And the adjacent side is the one right next to you. That isn't the hypotenuse. I mean, adjacent just means next to. It's that simple. Let's see this in action. Imagine you're standing at that bottom left corner. From that viewpoint, the side way over there, across the triangle, is your opposite. And the side right next to you is the adjacent. Makes sense, right? But now, watch what happens. If you just walk over to that other corner at the top, everything flips. All of a sudden, the side that was adjacent is now opposite you, and the side that was opposite is now right next to you, making it adjacent. This is the big aha moment. If you can get this flip down, you've honestly mastered the hardest part. Okay, on to section 3. So we've got our shape, and we've got the language to describe it. Now we can finally figure out what those famous, and maybe a little scary, trig words actually mean. Sine, cosine, and tangent. So here's the big secret. Sine, cosine, and tangent, they aren't magic. They're not some abstract, crazy concept. They are just names we give to 3 different ratios. They're just fractions, comparing the length of one side to another. And here's the real magic. For any specific angle, like, say, 30 degrees, that ratio is always the same. It doesn't matter if the triangle is tiny and fits in your hand, or if it's the size of a mountain. That consistency is what lets us measure the entire universe. First up is sine. The sine of an angle is just the length of the opposite side divided by the length of the hypotenuse. You can think of it as asking a question. Compared to its long, sloping side, how tall is this triangle? Next, we have cosine. This time, it's the ratio of the adjacent side to the hypotenuse. So if sine measures the tallness, you can think of cosine as measuring the wideness or the horizontalness of the triangle, again compared to that same long, sloping side. And last but not least, tangent. Now, notice something's missing here? The hypotenuse is gone. Tangent is the ratio of the opposite side to the adjacent side. It's a direct comparison of the triangle's height to its width. And you might already know that by another name, slope, or rise over run. All right, let's just pause here for a second and see it all together. Sine is opposite over hypotenuse, that's our tallness ratio. Cosine is adjacent over hypotenuse, our horizontalness ratio, and tangent is opposite over adjacent, that's pure slope. These 3 are our fundamental tools. Now, trying to memorize all of that, opposite over this, adjacent over that, it can feel like a lot. But don't you worry, because math has given us the ultimate cheat code, a tool so brilliant it packs this entire system into one easy-to-remember word. And this is it, SOHCAHTOA. Go ahead and say it out loud, it really helps. SOHCAHTOA.
Ka, Toa. This little mnemonic is the key that unlocks everything we just went over and makes it pretty much impossible to forget. Let's break it down really quick. SOH just tells you that sine equals opposite over hypotenuse. Ka tells you that cosine equals adjacent over hypotenuse. And Toa tells you that tangent equals opposite over adjacent. See? It's all right there, perfectly organized. So for our final section, let's actually put this awesome tool to work. Let's see how SOHCAHTOA helps us unlock a real trigonometry puzzle. Okay, picture this. You're looking at a right triangle. You know how long the side adjacent to your angle is, and your goal is to figure out the length of the side that's opposite your angle. So you have the adjacent, and you want the opposite. Which one of our three tools, sine, cosine, or tangent, are you going to use? The key is to just look at what you have and what you want. You have A for adjacent, and you want O for opposite. Now just scan your cheat code. SOHK, there it is, TOA. Which part of the code has both an O and an A? TOA does. And that tells you instantly, with zero guesswork, that you need to use the tangent function. It really is that straightforward. And that really just brings everything together so perfectly. Learning the definitions, opposite, adjacent, and hypotenuse, that gives you the map of the triangle. But SOHCAHTOA, that's your compass. It's what lets you navigate that map, pointing you in exactly the right direction every single time. So now that you have the compass, what are you going to go measure? Okay, let's be real for a second. The word sine, it can kind of make your brain just freeze up, right? It sounds so complicated, so abstract. Maybe it's something you were just forced to memorize back in school. But what if I told you we could completely rewire how you think about it, and we can do it in just a few minutes? Well, let's dive right in. I mean, really, what if all that complexity just boils down to a simple percentage? Just a number that tells you how efficient you are at doing something. Seriously, for now, just forget all the textbook definitions. This one simple idea, that's our key. That's right. We're not going to start with SOHCAHTOA or, any of those formulas. No. This is all about building a gut-level feeling, an intuition for what sine actually is and what it does for us. And here it is. This is the big idea, the thing that's going to unlock everything for you. From now on, we're going to think of sine as your vertical efficiency ratio. Yeah, it's just a measure of how much of your effort actually goes into gaining height. So, the crucial point is this. Sin is just a number. It's between 0 and 1. And you can totally think of that as a percentage, right? 0% to 100%. A high score, something close to 1, means you're super efficient at going up. A low score, close to 0, means, well, most of your effort is just spent going sideways. That's really it. You know what? Let's give it a personality. Imagine Salone as your personal verticality expert, like a super specialized contractor who only cares about one thing, height. This expert doesn't care about the total distance you've traveled, not at all. They just look at your path and they ask one simple question. Okay, for all that effort you put in, how much of it actually made you go up? Okay, so let's say you see this number. Someone says the sine of this angle is 0.5. Now, instead of that old feeling of panic creeping in, what should we think now? It's simple, really. It just means your vertical efficiency was 50%. That's it. For every, say, 10 feet you walked along some slope, you only went up by 5 feet. Half your effort went into gaining altitude. See? It's just a percentage. Nothing to be scared of. All right, now that we've got the core idea down, let's see it in action. We're going to explore 3 totally different stories that show how this one single concept, this vertical efficiency, applies in completely different worlds. This is where it gets fun. So for our first story, imagine this, a magical kingdom, the kingdom of slope, where every single road is exactly 100 meters long. It's the law. And the king, well, he's obsessed with height. He needs a really simple way to rate how much vertical climb each road gives you. Basically, he needs an efficiency score for his roads. And this chart, it shows the king's system perfectly. Look at road A. It's got a sine value of 0.1. That means it's almost flat. You walk the full 100 meters, but you only go up 10 meters. Now, road B is much steeper. Its sine is 0.5. So for that 100-meter walk, you get a full 50 meters of height. And road C? Whoa, that's basically a vertical cliff. It has a sine of 1.0, which means 100% of your travel is pure, straight-up vertical gain. Okay, fun as it is, let's leave the kingdom and jump into a real-world problem. Picture this. You're a crane operator. You've got a crane with a 100-foot arm. Your target? A window that's 80 feet directly above the ground. So, how do you figure out the exact angle you need? Well, an engineer isn't thinking in some abstract, complicated terms. Nope. They're thinking in ratios. It's simple. They have a path length, the arm, of 100 feet. They need to get to a height of 80 feet. So what's the required vertical efficiency? It's 80 out of 100, or 80%. All they have to do is find the angle that gives them a sine value of 0.8. See? They're literally just solving for a specific efficiency. Okay, for our last story, let's get super visual. I want you to imagine a big light source, like a projector, shining perfectly horizontal beams of light across a room. And you're holding a stick between that light and a wall. The height of the shadow that the stick casts on the wall, that is sine. This is such a great way to see the extremes. First, if the stick is lying flat, parallel to the light beams, what's its shadow on the wall? It's just a dot. It has 0 height. That's a sine of 0. But as you start to tilt that stick upward, the shadow gets taller and taller and taller until the stick is perfectly vertical. At that moment, the shadow's height is exactly the same as the stick's own length. You're getting 100% of the stick's length as shadow height. That's 100% efficiency. The sine is 1. Okay, so understanding this is one thing. That's great. But making it stick, so you remember it under pressure, like on a test, that's a whole other ballgame. So let's talk about a little brain hack to make this intuition permanent. The goal here is simple. We want to build a mental shortcut. We want to create a connection in your brain so that the instant you hear the word sine, you immediately think vertical. No hesitation, no conscious effort, just an instant link. And here's the hack. It's super simple. From this moment on, whenever you hear the word sine, I want you to picture an elevator. Just think about it. An elevator only cares about one thing: going up. It doesn't move left, it doesn't move right. It is the pure, perfect embodiment of vertical motion. Sine is the elevator. All right, you ready? Let's put this new intuition to the test. No calculators, no formulas, just your brain and this new idea. This is where you get that aha moment. Okay, so think about this. You've got a 10-foot ladder, and it's standing perfectly vertical, straight up against a wall, so it's making a 90-degree angle with the ground. How high up the wall does it reach? The answer, of course, is 10 feet. It's totally obvious when you're not getting bogged down by a bunch of formulas, right? And that is the crucial link. Because the ladder is perfectly vertical, 100% of its length is contributing to its height. Its vertical efficiency is maxed out. It's at its peak. And that's why the sine of 90 degrees is 1. 1 just means 100%, the maximum possible vertical efficiency. So let's wrap it up with a final protocol, like a mental checklist. Step 1, identify your total path length. The ladder, the ramp, whatever it is. Step 2, identify the tilt, the angle. Step 3, apply sine to that angle, which just gives you your vertical efficiency percentage. Then you just multiply your path length by that percentage, and boom, the result is your total vertical reach. Simple as that. So, we've firmly established that sine is the height maker. It's totally obsessed with all things vertical. Which, of course, leaves one last question for you to chew on. If sine is the expert on height, what do you think its sibling, the width maker, which you might know as cosine, is responsible for?
Have you ever thought about how some things in nature just grow without ever stopping? It's a pretty wild idea. So, how do we predict their future? Well, today we're going to crack the code of what's called continuous growth, and we're going to use a simple but seriously powerful blueprint to do it. Okay, let's dive in.
Believe it or not, right now, as you're watching this, a microscopic army is expanding. I'm talking about a colony of bacteria. And here's the thing, unlike us, they don't grow in little spurts. They grow constantly, every single moment of every single day.
So, how in the world do you predict the size of an invisible army? I mean, when something's growth is totally continuous, you need a special kind of tool. And lucky for us, we have one. It's a tool that lets us peer into the future of this tiny, growing colony.
And that tool is what we're going to call our growth blueprint. Now, its official name is an exponential function, but don't let that word scare you off. Just think of it like a secret code, and once we crack it, we'll have the power of prediction right at our fingertips.
Okay, here it is. This is our blueprint.
I know, it might look a little intimidating at first glance, but I promise you, every single part has a specific, simple job to do. So our mission today is to decode it, piece by piece, so we understand exactly how it all works.
First up, this P of T part. This is our target. It's our goal. It just stands for the population, the size of our army, at any specific time t that we decide to look at. It's the answer we're trying to find. Simple as that.
Next, we've got the number 100. You know, every army has to start somewhere, right? Well, this is our starting point. When the clock starts at time 0, we begin with exactly 100 bacteria. That's our baseline.
Now for this little letter E. This isn't just a random letter. It's a super special number called Euler's number. You can think of it as nature's secret ingredient for growth. It's this magic constant that just shows up whenever anything grows continuously, whether it's bacteria in a lab or even money in a bank account.
And this number, 0.05, that's our growth rate. Think of it like the speed limit for our bacterial army. It's telling us that our colony is getting bigger at a steady rate of 5% every single hour.
And finally, the last piece of our code, T. This one's easy. It just stands for time, and we're measuring it in hours. Now, this is the really cool part, because this is the piece of the puzzle we get to control. By changing T, we can tell our blueprint to predict the population at any point we want in the future.
Okay, the blueprint is decoded. Let's launch our first mission. We're going to use this formula to double-check something we already know. How many bacteria did we have right at the very beginning, when our timer was at 0?
Let's walk through it. First, we just plug in 0 for T. Easy enough. Next, we look at that exponent up top. What's 0.05 times 0? That's right, it's just 0. And now for a super important math rule. Any number, literally any number, raised to the power of 0 is always 1. So e to the power of 0 is 1. That means our final calculation is just 100 times 1.
And there it is, 100. The blueprint works perfectly. It confirms that at time 0, our population was exactly 100. Mission 1, success.
All right, now for the fun part. Let's jump in our time machine. For mission number 2, we are going to leap 10 hours into the future and predict just how massive our microscopic army has become.
Okay, so we follow the same steps. We plug in 10 for T. Now the exponent, 0.05 times 10, simplifies down to 0.5. For this next bit, you'll want to grab a calculator. E to the power of 0.5 is about 1.6487. So that leaves us with our final calculation, 100 multiplied by that number.
And that gives us about 164.87. But come on, you can't have 0.87 of a bacterium, right? So we just round to the nearest whole number. After 10 hours, our army has grown to about 165 strong. And just look at this comparison. It shows you the change so clearly. We started with 100, and in just 10 hours, that jumped up to 165. You can really see the quiet but relentless power of continuous growth right there.
So, we've seen the math work, which is cool, but why does this actually matter? What's the big deal? Well, this blueprint isn't just for predicting bacteria. It's a fundamental concept that helps us understand how things change all around us, in the real world.
This idea is at the very heart of calculus, which is really just the study of change. And once you see this pattern, you start seeing it everywhere. It's how your money can grow with compound interest, it's how a video goes viral online, and it's how scientists can do incredible things like predict how a virus might spread, figure out the right dosages for medicine, or even manage entire wildlife populations. It's basically the mathematics of momentum. All right, you've seen how the blueprint works. We've knocked out 2 missions together, so now I have a little challenge for you. It's your turn to take the controls and be the scientist.
So here's the question. What if that growth rate, that speed limit, was 0.10 instead of 0.05? In other words, what if the bacteria were growing twice as fast? After those same 10 hours, would you predict the population to be bigger or smaller? The power of prediction is officially in your hands.
Okay, so if you've ever taken a calculus class, you know that feeling, right? You're staring at a graph and something just feels off. Well, you are definitely not alone. Today, we're going to dig into the one single biggest misconception that's probably causing all that confusion. And even better, I'm going to show you a super simple mental trick to fix it for good.
It really all boils down to this one question. I mean, why do these graphs, which are supposed to make everything clearer, so often feel like they're actively trying to trick you? You see the lines going up and down and curving all over the place, but what story are they actually telling? Turns out the problem isn't the math itself, it's how our brains are hardwired to look at the picture in the first place. And that brings us right to the heart of the issue. There's this little mental battle that happens, probably without you even noticing, every single time you look at a calculus graph. I like to call it the map versus the graph. And, just understanding that this fight is happening, that's the key to unlocking everything.
So here's the deal. We all have this thing you could call a spatial bias. It means that when we see an x and a y axis, our brain just immediately, instinctively thinks of a physical map. X is east-west, y is north-south. We literally can't help it. And look, that instinct is great for navigating the real world, but in the world of calculus, it sends us completely down the wrong path.
This slide just lays out the whole conflict perfectly. On one side, you've got our gut instinct, what I'm calling map thinking. Our brain automatically sees the x-axis as east-west and the y-axis is north-south. And when it does that, the line on the graph looks like the actual physical shape of a road. But, and this is the big but, look at the calculus reality. Here, the x-axis isn't a place at all. It's the cause of what's happening. And the y-axis, that's the effect. So what you're seeing isn't a shape, it's the history of an event as it unfolds.
Right. So if x isn't a direction on a map, what on earth is it? This is where we get to the big reveal. It's time to unmask the true master variable of calculus. Let's just get this out of the way, nice and clear. That wiggly line you see in your textbook, it is not the road a car is driving on. It's not a drawing of the terrain. Not at all.
What they do show is the history of the trip itself. Think about it. Every single point on that line is like a little snapshot, a record of where something was at a very specific moment. You're not looking at a static map. You are watching a story unfold.
And boom, here it is. This is the absolute central point of this whole explainer. In the vast, vast majority of calculus problems you will ever see, anything involving motion or growth or any kind of change, that x variable, your horizontal axis, represents time. It's time. Time is the one thing that just keeps marching forward steadily no matter what else is going on. It is the ultimate independent driver of change in almost all of these systems.
Okay, so knowing that x is usually time is one thing, but really feeling it, making it intuitive, that's a whole different ballgame. And to do that, we're going to build a brand new mental model, using something we all use, probably every single day, a YouTube video player.
From this moment on, whenever you see one of these graphs, I want you to force yourself to stop seeing a static image. Instead, start thinking of it as a video file of the event that's being described. Seriously, this one little mental switch will change everything for you.
So here's how it works. That x in your calculus problem, that's just the scrubber bar at the bottom of the video. It represents time, and it's the one thing you can control. You can drag it forward or backward to any point in time you want. So then what's f of x? Well, that's the video screen. It's the output. What you see on that screen is totally dependent on where you decided to put that time scrubber.
And this table, oh, this is where it all just clicks into place. Look at this. When you see x equals 20 in a problem, all that means is you're dragging the scrubber to the 20-minute mark. Simple. That's your input. When you see f of 20 equals 15, that's just you looking at the video screen. It's showing you that at that exact moment, the car is passing mile marker 15. That's your output. And the derivative, f prime of 20 equals 60, this is the best part. That's the motion blur on the screen. It's how you can tell how fast things are moving right then. It's telling you that at that instant you were going 60 miles per hour. It all makes sense.
So that's a pretty powerful analogy, right? But what about the actual math? Why does this matter for the calculations? Well, let's take a look at how this new mindset makes a fundamental idea like the derivative suddenly become completely intuitive.
When you get right down to it, a derivative is just a ratio. It's asking a really simple question. If I nudge my input just a tiny, tiny bit, how much does my output change? That's it. And the answer to that question depends entirely on what your input actually is.
And here it is. This is the big payoff. If you're stuck in that old map thinking where x is a location, then when you calculate a derivative, you're finding something like speed per mile. I mean, what does that even mean? It's weird and confusing. But if you use calculus thinking, where x is time, then you're calculating the change in miles per hour. That's not just intuitive, that's the literal definition of speed. The whole concept just clicks into place perfectly.
Okay, so how do you make sure you get this right every single time?
I want to give you a really simple, practical tool you can use on any problem. Let's call it the check protocol.
It's really just a simple checklist. Before you even touch the math, just pause and identify the input variable. Ask yourself, what's the engine of this problem? What's the one thing that's causing all the other things to change? If the problem says something like, after 5 seconds, boom, X is time. If it says at 100 widgets produced, well then X is quantity. If it's at a $50 price, X is price. The rule is easy. Whatever's marching forward on its own is your X.
So really, the big takeaway is this. X isn't just some random letter from the alphabet. In calculus, it represents the prime mover, the independent variable that's driving the whole story of your problem. Once you figure out what X truly is, the rest of the math starts to tell a story that actually makes sense.
And that kind of leaves us with one final thought to chew on. We've just unmasked time as the secret master variable in so many calculus problems. But it makes you wonder, doesn't it? In economics or biology or computer science, what other master variables are out there, just hiding in plain sight, waiting for us to just change our perspective a little bit?
You know, what if I told you that one of the most intimidating subjects in school, calculus, isn't actually a math problem? In this explainer, we're going to reframe it as something you're probably already an expert at, a logistics problem. So let's just start with a really basic question. When you look at a calculus problem, what do you see? If you're like pretty much everyone else, your brain has been trained to immediately file it away as a math problem.
But that's the wrong classification. And that tiny little misstep is where almost all the difficulty comes from. The real challenge, the thing that trips most people up, it's not the calculation. It's how you classify the problem in the first place.
The breakthrough happens when you make this one mental shift. Just stop seeing calculus as pure math and start seeing it for what it really is, a logistics problem. Seriously, it's not about crunching numbers. It's all about organizing information and managing your inventory. So, how about we build this new mental model together? We're going to start with a core framework that, trust me, you already use every single day, probably without even thinking about it. Let's call it the inventory audit.
Pretty much any problem you face can be broken down into these 3 simple steps. First, you figure out what you have. That's your current state. Second, you define what you actually need. That's your desired state. And third, you find the right tool to build a bridge between the two. This simple audit is the key to, well, everything.
Okay, so let's see this audit in action. We'll compare a nice, simple static algebra problem with a more dynamic calculus problem. Now, the 3-step framework is going to stay the same, but the kind of bridge you need to build is completely different.
And right here is where we see the crucial difference. With the algebra problem on the left, it's kind of like assembling a desk. You have all the pieces you need, you just have to arrange them correctly. But with the calculus problem on the right, well, there's a disconnect. You have information about a car's position, but the question asks about its speed. There's a missing link, and creating that link, that is the entire point of calculus.
This really gets to the heart of it. Calculus isn't about scary equations. It's about recognizing that you need to transform your tool. You've got a position tool, but the job requires a speed tool. The whole challenge is just knowing how to build the right tool for the job.
So this is a great way to think about it, but let's get even more practical. We can actually convert this whole idea into a simple 3-step algorithm you can use to solve pretty much any calculus word problem.
Now, the first and most important step is to completely change how you even read the problem. You need to ignore the story, about particles moving or profits changing. Your job is not to follow a narrative. It's to be a data detective, hunting for 2 very specific clues. Here's that disciplined process. Step 1, you scan the problem just to extract the key data. Step 2, you identify your goal. And step 3, you execute the plan. Following these steps in this exact order will keep you from getting lost or, intimidated by the story. Okay, so during your scan, the very first piece of data you're looking for is the equation itself. Think of this as your map. It describes the entire landscape of the problem. We're going to call this the primitive function. The second piece of data you're hunting for is the specific value, like at time equals 3. This is your warrant, or your input. So if the equation is your map, this is the exact coordinate on that map, where all the work needs to be done. Step 2, identifying the goal, is usually the easiest part. You just have to scan the question for a couple of keywords. If you see words like rate, speed, velocity, or marginal, you know instantly what your goal is. you need to build that speed tool, which in calculus terms just means you need to find the derivative.
And finally, you execute. You take your primitive function, your map, and you apply the right transformation to it. For a ton of problems, this is a super simple mechanical process called the power rule. This is what turns your map into a speed tool. Then you just plug in your input value, and the rest is just simple arithmetic.
So let's bring this all together. When you start to use this framework, you really do fundamentally change your role. You're no longer just a student trying to find a single answer in the back of the book.
And honestly, this is the most important takeaway. Success in calculus isn't about being some kind of math genius. It's about being a disciplined inventory manager. It's not a talent you're born with, it's a skill you can absolutely learn. The truly difficult part, the real heavy lifting, is already done once you can check off these 3 items. Okay, I have my equation, I have my specific input, and I know I need the rate of change. Once your manager's checklist is complete, the actual calculation is just a final mechanical step. So when you embrace this mindset, you're not a passive student just being dragged for a problem anymore. You become the manager. You're in complete control of the inventory, the tools, and the whole process. So the only question left is, are you ready to manage your next problem?
Calculus. Just hearing the word can make you break out in a cold sweat, right? Well, what if I told you that you've been using it for years and you didn't even know it? Over the next few minutes, we're going to pull back the curtain and show you the simple math secret you already have mastered.
And this right here, this is the absolute heart of the problem. You know, we get so hung up on these crazy words like differentiation and integration, but the actual ideas behind them, they're shockingly simple. The barrier isn't the math itself, it's just the fancy language.
For most of us, this is the picture that pops into our heads, isn't it? You know, these impossibly complex equations on a chalkboard, something that only rocket scientists need to know. It just feels completely separate from our normal, everyday lives.
So let's just flip that whole idea on its head. Forget the rocket science for a second. Let's pivot from that intimidating myth to a simple, familiar reality. What if the big, scary secret to calculus was a word you probably use like a dozen times a day?
All right, get ready for this. This is what I like to call your per-epiphany, because the big secret, the shocking reality, is that you already do it. You have been using the core concepts of calculus your entire life. Sounds crazy, I know, but it's absolutely true.
So the key that unlocks the first and maybe the most important half of calculus, it's not some complicated formula you have to memorize. Nope, it's just a simple little word. You ready?
Yep, that's it. PR. This tiny 3-letter word is pretty much the secret handshake to understanding one of the absolute cornerstones of calculus.
I mean, just think about it for a second. Miles per hour, dollars per hour, beats per minute. You use these ideas all the time without even thinking to describe how fast something is changing.
Okay, and this is the big connection. This is the moment it all clicks. Every single time you use the word per, you are describing what calculus calls a derivative. You're talking about a rate of change. You're not just making small talk. You are literally speaking the language of calculus.
So if per is our secret key, let's give this whole idea a name that's a little easier to remember than derivative. So let's meet the slicer. This is our friendly tool for understanding this first half of calculus.
So what does the slicer do? Well, its job is pretty simple, actually. It takes a big total pile of something, say the total distance you've driven on a trip, and it slices it into one tiny, instantaneous moment to answer the question, how fast am I going right now? That is the derivative.
And trust me, there is no better, or maybe more painful, real-world example of the slicer in action than, yep, the dreaded speeding ticket. We've all had that feeling, right?
Now, this is where algebra and calculus part ways. See, algebra can tell you your average speed for the whole trip. Yeah, officer, I average 60 miles per hour. But calculus, our slicer, does something way more specific. It lets that police officer know your speed at one precise, instantaneous moment.
And that's the whole point, isn't it? Your ticket isn't for your average speed. It's for hitting 85 miles per hour at that one split second the radar gun caught you. That instantaneous speed, that rate of change right now, that is the derivative. You basically just got a ticket from the slicer. Okay, so that's the slicer. It slices a total down into a rate. So it only makes sense that the other half of calculus would do the exact opposite, right? So let's meet its twin, the stacker.
The stacker's job is the mirror image of the slicer's. It takes a rate, like your speed or your hourly wage, and it stacks all those little moments up over time to give you the grand total. This is what calculus calls an integral.
And the perfect, everyday example of the stacker in action is something we can all get excited about. Your paycheck.
It's so simple, right? You know the rate, you make $25 per hour, you know the time, you worked for 10 hours. Your brain just does it instantly. It stacks the rate over time to get the total, $250. And guess what? You just did calculus.
And get this, that super simple math you just did in your head, that is what has intimidated calculus students for generations. It's called finding the area under the curve. If you were to graph your $25 an hour wage, the area of that shape is your total pay. You just performed an integration without breaking a sweat.
And boom! Just like that, we're back to rocket science. This is exactly the same idea NASA uses. They take the rocket's speed, which is changing all the time, and they stack up every single one of those moments to figure out the total distance the rocket has traveled. It's just a way more complicated version of your paycheck.
Okay, so let's put it all on the table now. We've got the slicer, which finds the rate, and we've got the stacker, which finds the total. They're like this perfect two-way machine. But how do they fit together?
Okay, check this out, because this is the whole shebang right here. The slicer, which has the fancy name differentiation, takes a total, like your bank balance, and slices it into a rate, like your hourly wage. Its keyword is per. The stacker, or integration, does the exact reverse. It takes the rate and stacks it back up into a total. Its keyword is area.
They're perfect opposites, two sides of the exact same coin. One slices things up, the other stacks them back together. It's this beautiful, perfect system for understanding how things change over time.
So I want you to really let this sink in for a second. If you can glance down at your speedometer and understand what that number means, you are using the slicer. You get the fundamental idea of a derivative. You are already a calculus student.
And that's the big secret. Which leaves us with one last question for you. Now that you have this new way of looking at things, where else do you see the slicer and the stacker in your life? Think about your job, your hobbies. Where are you slicing totals into rates and stacking rates back into totals? Once you start looking, you're going to realize this math is absolutely everywhere.
All right, let's talk about the power rule. You know, that thing from calculus class? Today, we're going to tear it down and build it back up from scratch. We're going to turn it from this abstract puzzle into a tool, a real, practical tool that you'll actually get. So, let's dive right in.
So, first things first, I've got a question for you, and it's a big one. It's something that honestly trips up so many people when they dive into higher math. Here it is. Is an equation an answer? I mean, think about it. We're trained to see something like, y equals x squared, and our brain just screams, that's the solution.
But is it? Logically? No, it's not. An equation isn't an answer at all. It's a relationship. It's a definition. It's like a little piece of software, a set of instructions, just sitting there, waiting. Waiting for you to give it some data, an argument, so it can actually run. And trust me, getting this difference, the difference between the definition and the execution, that is the absolute key to unlocking calculus.
Okay, so to make this super clear, we're going to use a new framework. Let's visualize calculus as construction.
This is what I'm talking about, the two machines of calculus. On the left, you've got what I call the state machine. This is your starting point, your primitive function. Its whole job is to tell you about state. It answers the question, where are we, or how much do we have? But then, on the right, we build something new. This is the trend machine, what you know as the derivative. And this machine, it couldn't care less where you are. All it cares about is momentum. Its only question is, how fast is everything changing right this second?
So, the big question is, how do we actually build this trend machine? Well, it's simpler than you think. It's just a simple algorithm, a little recipe. We call it the drop and subtract rule.
Seriously, this is it. It's a super simple protocol. You take your term, you find the exponent, right? The little number up top. Step 1, you drop that number down in front to multiply. Step 2, you subtract exactly 1 from that original exponent, and bam, that's your output. You've just done it. You have built a trend machine using the state machine as your blueprint. It's that mechanical.
Okay, theory is one thing, but let's put this into action. We're going to run through 3 case studies and see how this framework holds up in the real world.
All right, first up, Case Study A, the physics of free fall. This is a classic. Just picture it. A heavy object, maybe a bowling ball, dropped from a high-flying drone. We've got an equation that describes exactly where it is at any given second.
Okay, now check this out. Look at how we've separated things. On the left is our state machine. F of x equals x squared. That is the rule for position. It's just a definition. Then we use our drop and subtract rule to build a trend machine. The 2 drops down, the exponent becomes 1, so we get 2x. That's our new definition, the rule for instantaneous velocity. And here's the crucial part. Only now, after we've built both machines, do we plug in the data. We ask, what's happening at 4 seconds? The state machine says, your position is 16. The trend machine says, and your velocity is 8.
And here's why that matters so much. Knowing the object has fallen 16 meters is, okay, it's useful. But the real magic, the deep insight, comes from that second machine. It tells us that at that precise moment, it's not just falling, it's accelerating at 8 meters per second. That's the trend. That's the momentum. See the difference?
Okay, let's switch gears completely. Let's talk business. Case study B, the economics of production. Picture a factory, right? And the more stuff they make, the more expensive each new item gets. It's not a straight line. It's a curve that gets steeper and steeper. We're going to use the exact same playbook here. The state machine, c of x equals x cubed. Well, that's just the rule for our total cost. Now, let's build the trend machine. Drop the 3 down, subtract 1 from the exponent, we get 3x squared. This is our definition for marginal cost. You can think of it as cost intensity. Okay, both machines are built. Now, let's plug in a number. 10 units. The total cost to make 10? $1,000. But the marginal cost? Whoa, it's 300.
And this is a huge deal. A CEO can look at the books and see a bill for $1,000. Fine, but what the trend machine tells them is that the whole system is getting stressed. The cost to make just one more unit is skyrocketing towards $300. Now that is information you can make a real decision with.
All right, one more. Case study C, biological growth. Let's imagine some bacteria growing in a lab. This one adds a tiny little wrinkle to the mix, a coefficient. That's just a fancy word for the number hanging out in front of the variable.
But you'll see our system handles this no problem. Our state machine is 5t to the 4th power. So to build the trend machine, we do the same thing. We drop the 4, but this time we multiply it by that coefficient that's already there, the 5. So 4 times 5 is 20. Then we subtract 1 from the exponent as always. Our new machine is 20t cubed. Simple. So let's run the numbers at the 2-hour mark. The population, let's say it's in thousands, so that's 80,000 bacteria. But the growth rate, our trend machine says it's 160, which means it's growing at a rate of 160,000 new bacteria per hour. Just let that sink in for a second. That is an absolutely explosive insight. The rate of new growth per hour is double the entire current population. This isn't just steady growth anymore. It's an out-of-control explosion. And that's the kind of urgency, the kind of critical trend that only the second machine can reveal.
Okay, to make sure this all sticks, let's quickly build a translation layer. We'll connect our machine language to the official math terms.
So from now on, when you see the word function, I want you to just think state machine. That's it. It's the static rule. It's the blueprint for position or cost or whatever, just waiting for data.
And the derivative? You know this one. That's our trend machine. It's that brand new tool we built from the function, the one that measures velocity or marginal cost or the growth rate.
And what does that trend machine calculate? The official term is the instantaneous rate of change, and that word instantaneous is key. This isn't some blurry average over an hour. It is the laser-focused, razor-sharp trend at one single point in time.
And if you're a visual person, here's how to picture it on a graph. The derivative is just the slope of a line, a tangent line that perfectly kisses the curve at that one single point. It's the geometric proof of the trend at that exact moment.
Look, if you take away just one thing today, please let it be this. You are not solving a puzzle. You're building a tool. Calculus isn't about some mysterious hunt for an answer. It's a straightforward mechanical process of building something useful.
So I'll leave you with this final idea. Think of the power rule as a refactoring process, like in programming. You are taking a piece of software that calculates location, and you are systematically rewriting it, refactoring it, into a completely new piece of software that calculates momentum. And once you can do that, well, that changes everything.